Okay, let's look at the next one. It looks like we have to put it in standard form, get a 0 on one side, and then factor this guy. So I'm going to move the two terms from the right to the left, and then I'll put it in descending order. And since I'm seeing 4 terms, I'm going to do this by grouping. So the GCF for the first two is an x squared. That leaves me with a 2x and a minus 1 when I take out the GCF of x squared. Then I got to be careful, I have a minus in the middle to factor out. And between 18x and 9, I have a 9 in common to pull out. That leaves me with 18 divided by 9 is 2. And since I pulled out a negative, this positive 9 turns into and let's not forget the x, to a minus 1. Again, this negative affected things because when I pull out a negative or factor out a negative, the signs switch. So the positive 9 became a negative 1. And then I see these in common. So I'm going to take out the GCF of 2x minus 1, and I'm going to have left these two guys, x squared minus 9. And this is further factorable, so I'll leave the 2x minus 1 as is. And I'll have an x plus 3 and an x minus 3. And finally, after all that work, I have it in the form that I usually need it, with everybody factored and a 0 on one side. That means I'm ready to pop out the critical numbers. If I set this inequality equal to 0, it pops out a half, a negative 3, and a positive 3. So on the real line, I go and I jot down all those critical points. It looks like I have a negative 3, a positive 3, and a 1/2. And that means I have 1, 2, 3, 4 regions to test. So I'm going to go ahead and test it in either here, doesn't matter, the original inequality when I got a 0 on one side, or the equivalent expression to that is the factored version. The factored version may be easier. In region 2, I like the number 0, so when I put 0 in the first parentheses of the factored version, I get a negative 1. In the second one, I get a 3. And in the third parentheses, I get a negative 3. Negative times negative is positive. So region 2 is positive. In region 1, let's say I pick negative 4. That's going to give me a negative 8 minus 1 when I put it in the first parentheses. That's going to be a negative 9 times a negative 1 when I do negative 4 plus 3 times a negative 4 minus 3 and negative 7. So these two are positive times another negative gives me a negative region. Over here, I think I'm going to pick x equals, what is that? That's a half. The next 1 would work. And if I do 1, I have 2 minus 1, which is 1. Then in the second parentheses, 1 plus 3 is 4. And in the third parentheses, 1 minus 3 is negative 2. So this region is negative. And the last region looks like it'll be positive. Let's say I pick to the right of 3, 4. Remember my critical points were negative 3, a half, and a positive 3. So if I pick 4 and I put it in the parentheses version, I have 8 minus 1, which is 7. 4 plus 3 is 7. 4 minus 3 is 1, so that's going to be a positive. And also, I could have known that these were going to be alternating because the multiplicity of each one of these factors is an odd number. Whenever the multiplicity is an odd number, your signs will alternate on both sides of that critical number. If any multiplicity is even, then on both sides you will have the same sign, either positive or negative. In any case, I was looking at finding stuff that is greater or equal to 0. So my inequality stuff has to be greater or equal to 0, which means positive stuff is greater than 0. So here's my solution, all the positive regions. In other words, I'm going from, and then since there's an equal sign, let's use a bracket, from negative 3 to, I guess, a half, close bracket, and then pick up again from 3 to infinity. So the solution to that inequality lies there. And let's go look at our TI and graph this thing quickly and see how that makes sense. So I have the original inequality 2x cubed minus x squared minus 18x plus 9 put in my y equals. It's actually after I moved it to the left and made it equal to 0. Now I'm going to go and see when there's positive stuff happening. So I go to the graph. If I do a zoom 6, it shows it, but it's a little bit off. It looks like it goes higher up and lower down. So let me just go to window and maybe have my y maximum and minimum change to like -20 to 20, let's say, and see if it picks up a better graph. Yep, it's better, but let me just go to window and make the y's go to like 30 for the higher. And now that looks like a third-degree polynomial that I was looking at, with the zeros -4, -3, and +3.5. Those are the critical points or x-intercepts we found. So I brought the image here in our notes so we can compare it to the solution we found by hand. Notice what happens is we were looking for the positive y values because it said greater than 0, and the positive y values happen here and then to the right. Those are all positive y values. And this was the number 3, so all these x values give you those positive y values. Or in this region, when we're between -3.5, we pick up those positive y values. And those are the exact same solutions we got when we did the real line and testing the regions. We got -3 to 1/2 and 3 to infinity, giving us positive y values. So basically for polynomials, you get a 0 on one side, and then you factor and you set it equal to 0 and get your critical points. Then you test the regions, and you can always confirm that by looking at your TI and seeing when the positive and the negative y values occur. Now let's go to rational functions. Rational functions, we can also deal with inequalities there. They're done the same way pretty much, but they may have vertical asymptotes, as you saw in section 3.6, and so those cut the graph in separate regions and also contribute critical points. So here are the steps we're going to do them by hand, and then look at our TI also. So again, first we're going to get a 0 on one side, just like we did with polynomials. So we'll basically have our fraction greater or equal to 0, let's say, or less than or equal to 0, or whatever the inequality may be. Then you're going to set the numerator equal to 0 and the denominator equal to 0. And those are going to be your critical points. So both contribute here. In a polynomial, it was only one expression. Now you have a numerator and a denominator to worry about to get the critical points. And then step 3 is the same as before. Test regions and keep either the positive or negative depending on what the problem asks you. So everything is pretty much the same as polynomials, with the added step of the vertical asymptotes from the denominator also contributing critical points. Let's go look at an example. It says solve the inequality. Clearly it's a rational function, and we already have the 0 on one side, so we're good to go, which means I just have to get the critical points from the numerator set to 0 and the denominator set to 0. So this one is going to give me, it looks like a 7/3, and this one's going to give me a -2. So I go to my real line and I mark those 1, 2, 3, 4, 1, 2, 3, 4. So I've got 7/3 a little bit to the right of 2. That's like 2 1/3. And then -2 is here. And now we're going to go test the 3 regions the way we did with polynomials. And so easy number in the second region is 0. I go put it back in the original, and there I have -7/2, so I guess that's going to be a negative number. Then on the right, let's say I pick x equals 3. That's going to be, if I go in the original, 3 times 3 is 9, minus 7 is 2, over 3 plus 2 is 5. That's a positive. And we expect the left side to be positive too, because they were all multiplicity of 1. But we'll go test it anyway. If I do like x equals -3, in the original I have 3 times -3, which is -9. Minus 7, that's minus 16, over -3 plus 2 is -1, so that's going to be a positive. And my original problem said, give me the stuff that's less than or equal to 0. So the stuff that's less than or equal to 0 means give me negative stuff. So I'm only interested in this region for the solution. And I guess we're pretty much there. The solution is between -2 and 7/3. I just have to be careful because when x is equal to 2 or -2, the denominator becomes 0, right? And I can't have a denominator of 0, so I cannot include -2 in my answer. I must leave it open despite the fact that this has an equal sign in it. Even though it has an equal sign, I'm okay to leave the 7/3 closed, but the -2 cannot be closed. Closed means include the -2, and -2 will make things undefined. So the solution for this rational inequality, I guess, is from -2 to 7/3 is when this rational inequality is less than or equal to 0. Now let's go look at the graph of this on our TI and see why that makes sense. So we've got 3x minus 7 in parentheses divided by x plus 2, and I'm going to do a zoom 6 for a standard window. And that's what my graph looks like. We know it's got a vertical asymptote, we know it's got horizontal asymptotes, we know all that stuff from the previous section, but now let's go look at the inequality. All right, so we know again that there's a -2 vertical asymptote, and we also know since the degrees of the top and the bottom of it are the same, the leading coefficients 3/1 give us the horizontal asymptote. But this problem says, hey, give me the stuff, all the y values that are negative. So all the y values that are negative basically happen over here. Because aside from that little piece, everybody else that's over here and over here, those are positive y values because they're above the x-axis. So I'm not looking for those. I'm looking for that region, the yellow region that I've highlighted, and that yellow region that's negative y values, because that's what my original problem was saying, hey, keep the negative y values. Notice the x values that gives me those starts at this value of 7/3. So in this little segment, all these x's are producing these y values. So 7/3 is the right edge of the x's, and the left edge has an asymptote, so it gets closer and closer to -2, but never equal to -2. So basically that little region, all the y's are negative, and they occur between the x value of -2 and positive 7/3, which is what we got by testing the regions. We'll look at maybe one more example in the next video.